the example of Hess's law. And then we have standard enthalpies of formation. Now, each and every substance that we found in nature, it involves a certain amount of enthalpy of formation. But some of these exist in nature, they do not have any enthalpy. Specifically, some gases that we come across, or some of these naturally found metals, they don't have enthalpies of formation. It's going to be zero. So I will show you some examples. For here, for example, bromine Br2 is 0. That's how it exists in nature. Bromine liquid, that is 0, but bromine gas has delta H 30.9. Calcium, one element solid, 0. But calcium oxide, it's a combination of two elements, but that involve a formation of enthalpy, which is negative 635. Calcium carbonate also has negative 1206. If you take carbon, carbon exists in nature as graphite, so that is 0. But for diamond, carbon has to process to become diamond, that has a number. And similarly, all of these other compounds, if it is a combination of more than one type, that would be involve enthalpy of formation. But if it is a diatomic molecule, chlorine, 0. And then similarly, hydrogen gas, 0. And liquid mercury, that is how it exists in nature, so that is also 0. Nitrogen, 0. Oxygen gas, 0. So likewise, enthalpies of formation you can find from this table. Okay. Some are going to be exothermic, some are going to be endothermic. Exothermic ones releases heat when it formed. That's why you see negative values. And endothermic ones would be positive. They absorb heat when they form these substances. Okay. So these are the standard enthalpies of formation. And then with that formations, we can write formation equations. Normally, any compound will be formed by its elemental form. Now, write a balanced formation equation for each of the following and include the value of delta H naught F. Delta H naught. Here, the delta H naught represents the standard conditions. F is the formation. So, silver chloride solid. Now, we are going to form silver chloride, AgCl. How does silver chloride form? What are the substances it needed? It needed silver. How does silver exist in nature? As a solid. And then chlorine. How does chlorine exist in nature? As Cl2 gas. So you have to specify it is state, gas, solid. And then it is going to form one silver chloride, 1 mole. So then the Cl2 is 2. So you write half Cl2. That is how you write the formation equation for silver chloride from its elemental form. Okay, and include the value of delta HF. So how do you find delta H formation? You go to here, silver chloride. Where is silver chloride? Do we have it here somewhere? AgCl, yes we do. Do you see that? Silver chloride solid, that's the number value. So it's negative 127.0. So after you write the equation, you write delta H equals negative 127.0 kilojoules. That is how you write a formation equation. And then the next one, formation of calcium carbonate. How do you form calcium carbonate? What do we need to form calcium carbonate solid? What elements you need? You need calcium. How does calcium exist in nature? As a solid. And then the carbon. Carbon is also graphite, or you can consider solid. plus the oxygen O2. How does oxygen exist? As a gas. Now calcium, carbon, oxygen, and we also need to make sure that they are stoichiometrically balanced. One calcium, one carbon, but there are three oxygens. How do we make it three oxygens? You put 3 over 2 at the front. That will give you 3 oxygen. Okay, you have to specify their states: calcium solid, carbon graphite, oxygen gas, and then proper number of moles. And the one last thing we need to find out is the calcium carbonate enthalpy of formation. Calcium carbonate, this number, solid, negative 1206.9. Negative 1206.9 kilojoules. That is the delta H. So that's how you write a formation equation. And then the last one that you need to write the formation equation is HCN, hydrogen cyanide. How do you form hydrogen cyanide? It's also given here. Hydrogen cyanide will be formed from hydrogen, carbon, and nitrogen. Hydrogen exists as a diatomic molecule gas, so H2 gas, carbon graphite, nitrogen gas. And it needs to be one hydrogen, one carbon, one nitrogen. But it does exist as H2, so then it need to put as half H2. One carbon, half nitrogen. And from the table, you can find out what is the value for HCN, hydrogen cyanide. Do you see that? Hydrogen cyanide, positive 135. So you can write that down. Delta H formation 135 kilojoules. So that is how you normally write balance formation equation for any compound and include the delta H formation value. Okay. We have only one small thing to do, but let's see if we can do it over here. Okay, calculating delta H for a reaction from delta H formation values. Earlier we learned how to find out the how to write the equation for delta H formation of a one particular compound. But in a reaction it involves several compounds. So then we need to know how we can find out the delta H reaction, meaning what is the delta H value for the whole reaction from the delta H formation values. Let's see here. Nitric acid is used to make many products, including fertilizers, dyes, and explosives. The first step in its production is the oxidation of ammonia. Ammonia with 4 ammonia molecules with 5 oxygen, giving you 4 nitrogen monoxide and 6 water molecules. We're going to find out the delta H reaction from delta H formation values. And this is the formula that we're going to use. Delta H reaction, meaning for the whole reaction, delta H value going to be, this symbol represents the sum of all the delta H formation values for the products minus the sum of all the delta H formation values for the reactants. Now in our example we are looking at what are the products: nitrogen monoxide and water. We also need to consider the molar ratios 4 and 6. So your products, delta H values for the products, subtract the delta H values for the reactants. 4 ammonia molecules and 5 oxygen. These two going to be your reactants. And then the delta H formation values we can find from the table. Okay. Okay, so delta H reaction going to be sum of all the delta H formation values for the products minus the sum of all the delta H values for the reactants. And our products are nitrogen monoxide and water. There are 4 nitrogen monoxide molecules. So 4 number of moles 4 times the delta H values for the nitrogen monoxide. and for the water 6 water molecules. So number of moles times the delta H value for the water. Subtract the reactants enthalpy values, 4 moles ammonia, 5 moles delta H value for the oxygen. And we need to find out delta H formation of nitrogen monoxide. Let's look at our table and see nitrogen monoxide gas. Do we see nitrogen monoxide gas here? We do. Do you see that? Nitrogen monoxide is this one, 90.3. So you write that one down, 90.3. And what else we have? We have ammonia. Do you see ammonia NH3? Yes. Negative 45.9. We need that value too. What else? Water. Water was the water gas or liquid. We do have two numbers. You see here water gas and water liquid. So if the water was gas, so we're going to use this number. We need this number, and we also need oxygen. Oxygen should be 0, but we need to show it to you. Where is oxygen? Do you see? Yeah, I do see oxygen. So this is oxygen right here. It is 0. So the ones that I have circled in green, we need these values because that involve our reactants and the products. So you take those values, you plug in those numbers here, over here. So 4 moles times nitrogen monoxide enthalpy 90.3, and then 6 moles. 6 moles times the value for water, gas, to negative. That's a negative number, so you have to put that number as well. You take that two numbers and you subtract the reactants. 4 times ammonia, negative 45.9 kilojoules per moles, and 5 times oxygen is 0. So when you do that calculation, you can find out the enthalpy of the whole reaction from the formation values. That's how you do that, and then calculate the final amount, negative 906 kilojoules. Okay, that's how you calculate. So this is showing it here in a graph form, how you calculate delta H reaction from the sum of the enthalpy values for the products minus the sum of the enthalpy values for the reactants. Okay, we can conclude this section over here.